Welcome to Jones Math Ed Problem Solving with Dr. Jones and Lucy. Today we're talking about prime numbers. And Lucy, we're going to talk about how to find out what numbers are prime, and then we're going to get to talking about how many prime numbers there really are. Okay? So, first question I have is we're going to look at this thing. This is an old technique called a sieve. This is technically called the Sieve of Eratosthenes. And Eratosthenes was, he has a Greek name, but he lived in Alexandria, Egypt. And he came up with this way that's kind of a quick way to determine if numbers are prime or not. Do you know what a sieve is?
Yes.
What is a sieve?
It's where you sort out things.
Okay, so kind of like this. I have one from my kitchen here. This sorts out the water from the pasta is what we use this for in our house. You might call this a strainer or a colander. So that's what a sieve is, if that's not familiar. This one is arranged in columns of 6, so that on the very right column, all of these numbers are multiples of 6, and that just kind of makes our work a little bit easier. So this is going to help us find prime numbers. Why did I cross out the 1?
Because 1 cannot be a prime number.
1 is not prime, and 1 is also not composite. So here's how the sieve works. Eratosthenes came up with this algorithm, or this routine. So pick a color that you like.
I will use this color.
All right. Circle the next number that's not crossed out, so that's 2.
2.
And now cross out all the multiples of 2.
Basically this entire row.
Okay. So that entire column got crossed out. Any others?
This column.
That column right there, except for the 2. Yeah, good.
And this column.
Yeah. So this is kind of cool that since we arranged it in with 6 rows, that the second row, the 4th row, and the 6th row, all of those are even numbers, so none of those except for 2 are prime. Okay, now go ahead and pick a different color.
Okay. I shall use this color.
All right. Circle the next number that's not crossed out, or the smallest number that's not crossed out. Okay.
Right.
And now, before you start crossing out multiples of 3, so what this means is 2 is prime and 3 is prime. Before you start crossing out multiples of 3, I want us to think about what's the first multiple of 3, or what's the smallest multiple of 3 that's not already crossed out?
9.
9. 6 is a multiple of 3, but we already crossed out 6. But we have to cross out 9. So go ahead and cross out the multiples of 3. What are you thinking?
Is this entire row just going to be...
That entire column you think is going to get cut out? Yeah. So if we do 3 times 2, we get 6. That's already crossed out. 3 times 3 was 9. 3 times 4 was 12. That was already crossed out. Basically, 3 times any even number is already crossed out here. 3 times the odd numbers, 3 times 5, 3 times 7, 3 times 9, 3 times 11, 3 times 13. And another way to think about this is if we count every 3, 1, 2, 3, that's a multiple of 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. We keep ending up either in the row, in the column under 3 or in the column under 6. Okay, pick another color. All right. Circle the next number that's not crossed out, and then so that means 5 is a prime number. And I know earlier I said this was a fast way, and it probably doesn't seem fast, but we're almost done. Our list goes up to 200. So this is going to show us all of the prime numbers that are less than 200. Before we cross off the multiples of 5, what's the first multiple of 5 that we have to cross out because it's not already crossed out?
25?
25, yeah. So with 3, it was, you remember which one we had to cross out for 3?
15.
No, I'm sorry, not the multiple of 3. When we were using the purple marker,
9.
we had to cross out 9. And what was the first number we had to cross out when we were working with 2?
4.
4. Okay, so this time go ahead and cross out. You've already got 10 and 15 and 20 crossed out. We have to cross out 25. How are you getting these so fast? What are you thinking?
Well, at first I was just crossing out everyone that had a 5.
Okay. Yeah, right.
But because the ones with the zeros would have already been crossed out.
Okay.
But then I noticed that these are all 5 apart.
Oh, interesting.
And the 5th one is going to be a multiple of 5.
Okay. Great. So there is this pattern with 5s. It's not down a column like it was with 2s and 3s, but it's kind of diagonally. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, like that. And I like the pattern you saw as well, where we were skipping. It was every 5th one down. Okay. Pick a new color. Circle the next number that's not, the smallest number that's not crossed off. 7. Okay, that means 7's prime. Now, again, what's the smallest number we're going to have to cross off that's a multiple of 7 that's not already crossed off?
$49.
49, okay. Yeah, 14, 21, 28, 35, and 42 were already crossed off, but 49. So now, this is a 7, the first one we had to cross off was 49. With 5, do you remember which one was the first one we had to cross off?
25.
25. And with 3, do you remember which one?
9.
And with 2?
4.
4. Okay. All right, so go ahead and cross out 49. And now we're looking for multiples of 7. That was 7 times 7. Is that right? Are you counting down 7?
Mm-hmm.
Okay. So 91, that's a good question for a calculator. Is 91 a multiple of 7? What will we type in the calculator to find out if 91 was a multiple of 7?
91 divided by 7.
And
13.
that gives us a whole number. Okay,
yes,
yeah, that's great.
I was right.
All right. Okay, keep going. $133. I'm checking on the calculator because I don't know my... Oh, 19. Okay, great. Where do you start with on that? Where's a multiple of 7 in that row on that column under 5?
35.
77. Is that a multiple of 7?
Yes.
Okay. 119 divided by 7 is 17. Yep. 161 divided by 7 is 23. Yep.
And those.
Okay. And then the 7s, they're actually in a diagonal pattern as well. 7, 14, 21, 28, 35, 42. That's because 7 is one more than 6. So you go over, when you go over 6 and then one more, you get to that next one. So they're in a diagonal pattern. Okay. Take another color and circle the next number that's not circled yet, not crossed out. That's 11. So 11's a prime number. What's the first one we have to cross out for that? Do you know your multiples of 11?
Yes.
What are they?
11, 22, 33, 44, 55, 66, 77, 88, 99, 110. So I guess it would be
So you're at 110.
then it would be 115.
Is that a multiple of 11?
I don't know. No.
No. Okay. So 110 was 10 times 11. Checking 121. Yep. So with 11, the first one that we have to cross off that we haven't crossed off is 121. So go ahead and cross off 121. And then one way to do that is to just add 11 to that number. So 110 plus 11 is 121. 121 plus 11.
132.
Okay, plus 11.
143.
Okay, plus 11.
154.
Plus 11.
165.
Plus 11.
176.
Plus 11.
187.
Got to get that one crossed off. Plus 11.
198.
Okay, and that plus 11 is bigger than our page, or bigger than the numbers on our page, so we'll stop. Okay, do you notice a pattern with the prime number and the first one that we need to cross off that's not already crossed off? Do you see any relationship between the number and the, what is it?
The number squared.
2 squared, 3 squared, 5 squared, 7 squared, 11 squared. Nice insight. So go ahead and take another color.
That's all our colors.
Okay, use this one because we haven't used that one yet. Take that and circle the next number that's not crossed off.
13.
13. So the first one, according to this pattern, we've already got 13 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 crossed off. So 13 times 13 is 169. So cross that one off. And then if we add 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, we would need to cross 182 off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Need to cross off 195. And 13 more would be off of the page, so I don't need to do that. Okay? Use that same color and circle the next number that's not crossed off.
17.
What would be the first number we'd have to cross off for 17? 289. But that's not even on our page. So our page only goes up to that. So that means, you know what that means about all the numbers that we haven't circled or crossed off yet?
They're all prime.
They're all prime. So go ahead and circle the numbers. Use that black marker that aren't crossed off yet. So 19, 31, 37, 43, 61, 67, 73, 79, all of these numbers. 127, 139, 151, 157, 163, 181, 193, 199. Those were all in the column under 1. And then 23, 41, 47, 53, 59, 71, 83, 89, 101, 107, 113, 131, 137, 149, 167, 173, 179, 191, 197, and
yeah,
29. So I have this question at the bottom, which I don't really, it's there, so sometimes I ask this question. Where do most of the primes lie?
The ones column.
In the column under 1.
The fives column.
In the column under 5. What that means is if you take a number like 23 and you divide it by 6, you get a remainder. So 23 divided by 6, or 23 divided by 6 is what? It's not a whole number. What would we get? What is the whole number part of the answer?
23 divided by 6 is 3.
3, okay. But there's a remainder.
Of 5.
Of 5, yeah. Okay, look at the number 29 that's under it. 29 divided by 6 is what? What's the whole number part? What's the quotient?
Four.
Okay, what's the remainder?
5.
What about 35? What's 35 divided by 6?
5.
What's the remainder?
5.
Do you notice anything in common here? Notice any patterns?
The remainder is 5.
Because we're under 5.
In the fives column.
Okay.
That is a crown.
If I pick a number like 43
43.
and divide it by 6, I'm dividing by 6 because I have 6 numbers, 6 columns.
Yes.
43 divided by 6,
43 divided by 6.
what's the quotient?
Is 7.
With a remainder?
1.
Yep. So these numbers here have a remainder of 1 when we divide by 6. These numbers here have a remainder of 5 when we divide by 6. I want to take this equation. That 7 is the quotient, and that 1 is the remainder. And I want to rewrite this. I want to rewrite as 43 equals 7 times 6 plus 1. Does that notation make sense to you?
Yes.
Okay. And I could also, I'll take this statement for 23 and I'll rewrite it as 23 is 3 times 6 plus 5. Does that make sense?
Yes.
All right. So now I want to show you this other thing that a different Greek person who had a different name, but it started with E, and his name was Euclid. And I want to show you how Euclid came up with a Euclid's way of finding out how many prime numbers there are.
That's wacky.
Euclid had this idea that there were a certain number of prime numbers, or he was wondering about it. Like we got some, is this, the 199 was the largest number we listed.
Mm-hmm.
Is that the biggest prime number?
No.
How many prime numbers do you think there are?
Well, as numbers are infinite, so should be the prime numbers.
Oh, that sounds really deep right there. Okay, so what Euclid did is he said he had this idea that every number that's greater than 1 anyway, every number greater than 1, every whole number greater than 1 is one of two things.
number or a composite number.
A prime number or a composite number. It's either prime or it can be written as the product of primes, which is another way of saying it's composite. So Euclid's idea was, he used that idea and he said, let's imagine we have this list of primes here. List of primes. And let's say we know that 7 is on that list.
Yes.
I mean, we have a big list of primes here, but Euclid didn't start with that big list. So 7, is that prime? Don't write on that. I need to write here. Okay, 7's prime. So it's prime, so that means what we're going to do is we're going to add 1. So this is another routine. And that gives us 8. Is 8 prime?
No.
Okay, but we can write 8 as the product of primes. What prime numbers multiply together to give us 8?
2.
2 times 2 times 4 is 8, but 4 is not prime.
2 squared.
Okay, or 2 times 2 times 2. So this, or 2 to the third power. So this gives us another prime to put on our list. Now we know that 7 is prime and 2 is prime. So then what Euclid does is he takes the primes on his list, he multiplies them together. 14, that's obviously composite because we multiplied things together. And then he adds 1 to it. The reason why he adds 1 is that means that this result that we get, if we divide it by 7, we're going to get a remainder of 1. If we divide it by 2, we're going to get a remainder of 1. What is 7 times 2 plus 1?
7 times 2 plus 1 is 15.
Okay, is 15 prime?
No.
Can you write it as the product of primes? So before I talk about 3 times 5, if we take 15 and divide it by 7, notice we get a remainder of 1. If we take 15 and divide it by 2, notice we get a remainder of 1. So now we have 2 more prime numbers on our list. So Euclid's method says now take 7 times 2 times 3 times 5 and add 1. Five times 2 times 3, we need to multiply by 7. Plus 1, that's 211. 211 is just a little bit too big for my list here. What I do know is that if I take 211 and divide it by 7, I'll get a remainder of 1. If I divide it by 2, I'll get a remainder of 1. If I divide it by 3, I'll get a remainder of 1. If I divide it by 5, I'll get a remainder of 1. So now the question is 211 prime or composite? Before we answer this question, I'd like to think about this idea here, about if we take a number like 36 and we list the factors. 36 is 1 times 36, 2 times 18, 3 times
12, 4 times 9, 6 times 6.
Great. Notice that then the factors, as they were getting bigger here, they loop around and go bigger as we go up. The halfway point, if we're talking about that, is 6. If we pick another number like, let's say 20, 1 times 20, 2 times 10, 3 times, no, not 3, 4 times 5, and then we're done with that. Or if we pick a number like 23, we have 1 times 23, and we're done because 23 is a prime number.
Yay!
How does 6 relate to this, where I turn around? How does that relate to 36?
36 is 6 squared.
36 is 6 squared. Or the square root of 36 is equal to 6. right?
Mm-hmm.
What number squared would give you 20? Or what's the square root of 20?
The square root of 20 is...
Well, what's it? I don't really care what it is exactly. What's it between? What whole numbers is it between?
4 and 5.
So it's 4 point blah, something right there. Notice that 4 point something is where we turned around, where we stopped going down this column and turned around. What's the square root of 23? Or what whole number is it just a little bit bigger than? Square root of 23.
5. No.
What's it between? What whole numbers is it between?
4 and 5.
4 and 5, because 4 squared is 16 and 5 squared is 25. So 4 point blah. Okay, so here's what we can do. With this 211, I know it's not divisible by any of these numbers. And now I have this nice list that you created. And so I can check, but I only have to check up to where the square root of 211 is. So why don't you ask the calculator what the square root of 211 is. So I really only need to look up to 14, but then again, I really only need to check the prime number. So I know I don't have to check 2, 3, 5, or 7, because those were in my list and they all have a remainder of 1. So let's try 11. 211 divided by 11. Nope. 211 divided by 13. Nope. And 13 is, we don't have to check 14 because that's a composite number. Or 5, we don't have to check the composite numbers. I just told you we don't have to check the composite numbers. And that, look, check this out. The 17 that you've got is bigger than the quotient of 12. So so what that means is, since that square root of 211 is like 14 point something, we only have to check the prime numbers that are less than 14. So that means 211, the only way we can get it is 1 times 211. So that means that is a prime number on our list.
And it's also wacky.
So Euclid's method would then do, what do you think he would say to do next, for the next step?
Multiply all those together and add 1.
So that would be a big number.
Yeah.
7 times 2 times 3 times 5 times 211 plus 1.
And the
44,000, hang on just a sec, let me write this down. 311.
And the square root.
We could now figure out the square root, but Euclid's idea was this. This will go on forever, so there are an infinite number of primes.
I was right.
Good. Great. Thanks so much. That was really cool.
You're welcome.